And so it'll eventually reach what's known as electrostatic equilibrium. And the advantage of this, of what we're about to talk about, is that sometimes if you know an object's going to be in electrostatic equilibrium, and eventually, without interference, it will reach that state, a conductor will reach that state, is it'll give you some shortcuts in order to solve problems. Or, more directly, I've asked questions where I've given a strange shape. I said, a bunch of excess charge, can put it on it. Once it reaches electrostatic equilibrium, where are the charges distributed? So rule number one, higher concentration and I say rule number one, it's not like Newton's laws where, you know, there's a list that everybody goes by, it's just, it's the order in which I'm doing it. Higher concentration, at smaller internal radiuses, or radii of curvature.
Dr. Fox?
Yes?
So if it was a circle for the surface, would it all stay evenly distributed?
Yes, it would. So if I have a shape like that, realize I have a pretty small radius of curvature here, but that is a small external radius of curvature, assuming that inside and outside. This is an external radius of curvature. So if this were my conductor, most of it would be concentrated probably, I'm going to guess, get a big concentration here, here, a little less there, might be a big concentration there. You'd have practically no excess charge here because it's a huge internal radius of curvature.
You mean external there? Huge external radius curvature?
It's a small external but huge internal.
Oh, yeah, okay.
Another rule. Now I started out with a distribution of charges all around the edges. Oh, pause here. Questions? Harrison, was your question answered?
It was, yeah. I got the small. I thought it was larger internal. I just mixed it up. So now it makes sense. Yes.
Okay. Other questions? Now I started out this with a whole concentration of electrons here, but I could change my scenario using the magic of the finger there, and I can start out with all the charges concentrated in one corner. It's a conductor, so the electrons can move freely. What's going to happen if I put all the charges in one spot?
They'll move to the other corners, right? They'll move to the rest of it.
It'll eventually end up looking like that again. And so, let me throw in the words, I've been talking about it, but didn't actually write it. Conductor. We're talking about conductors in electrostatic equilibrium. That excess charge resides on the outside, or on the surface, I should say. Resides on the surface.
Is it entirely proportional to the angle? Like if you were to have a triangle that has two longer sides and one shorter side, is that an isosceles triangle? I don't
So
know.
if I had a sharp
I
point,
think so.
Yeah, like it has a sharper peak. So the narrowest angle would be at the top and these should be slightly larger. And let's say you had like the angles and the sides, would the two angles at the bottom have the same number of electrons and this would have much more because it's a smaller angle, but is it like proportional to the angles? Like, is it that mathematical? Or is this just a conceptual thing?
I'm doing just conceptual here. Is it directly proportional, or I guess inversely proportional? The smaller the angle, the greater the concentration.
Right.
I don't know. Trying to think if there's a simple way of looking at it that would give that answer.
Like, let's say the side length down here was 30 centimeters and each of these sides were 60 centimeters. Would there be, I guess it would be twice as much.
If the angles were the same, they would have the same, should have the same concentration.
Yeah.
But if, for the one that's much skinnier, I suspect that it's not directly proportional to the angle, but more likely directly proportional to the sine, if it's gonna be directly proportional. But,
If you don't immediately know, then it's not something we necessarily need to know, and I'm
Yeah.
okay with that.
yeah, I don't know immediately.
That is fine.
The electric field inside the conductor, again, once the conductor is in electrostatic equilibrium, electric field inside is equal to 0. This goes hand in hand with the residing on the surface, because if I have a conductor, and let's say the electric field is not 0. If I have a charge inside and the electric field is not 0, what must be true about what's happening to that electric charge? Or an electron, as I have listed in this particular example.
Could you repeat that one more time?
If I have a conductor here, and if the electric field is not 0 in the middle, and I put a charge there, what would happen to that charge?
It's gonna move either towards or away from wherever the electric field is.
Okay. If I have an electric field going in that direction, the electric field, this electron would be moving in the opposite direction. In essence, that electron is going to have a force applied to it. And so that electron will have that force applied to it until there are no more, until the electric field inside is 0 again. If the electric field is not 0, there's going to be forces applied to charges, which means it's not equilibrium. So, in this scenario, internal the electrons will be forced to move until the electric field inside is 0. Protons will be forced too, but they're not going to move. Once they are residing on the surface, the electric field at the surface is perpendicular to the surface. Because you're basically going to be forcing these electrons to move around until the only force, the net force acting on the charges at the surface has to be away from the surface. This is going to move until the net force acting on it is this way, when that point when it can't escape. And so the electric field at the surface is perpendicular at that point of contact. Or in the strange shape here, once it's in the electrostatic equilibrium, the electric field at that point is going to be like that. At this point, it's going to be like that. And so on. And now I'm going to ask you to reach back into energy work, more specifically dot products. If I have an object being forced in this direction, so I have some force, but the movement is this way. What can you tell me about the work being done on the object?
It's greater than the force.
How's that?
Because, well, then that,
Did you stop mid-sentence or did
I did.
Okay. Oh, let's drop back. Oh,
The work would be equal to 0.
Why?
If the displacement is to the right, if the force is up, then it's not doing work on the object, otherwise the displacement would be heading somewhat in that direction.
Work is the dot product between force and displacement. Dot product is multiplying parallel components.
Right.
If it's all perpendicular, work is 0. So it takes no work to move an object perpendicular to the force. So if I can move an object from this point to this point and doing no work, well, I know that the force is either parallel or anti-parallel to the electric field. So if the movement is perpendicular to the electric field, no work is being done. If you think about, if I have some object sitting right here, somehow make it magically hover, there's a gravitational pull on it downwards. If I give the object a tap and it starts moving this way, there's no work being done on it once I've tapped it. Once I tap it once and then it starts moving sideways, no work is being done. The potential energy at this point and the potential energy at this point are the same. These lines here with equal potentials. And I do want to point out, I'm not saying potential energy here. My example, I use potential energy to just give you some sort of image here of something you've dealt with before, but this is potential, this is electric potential. Lines with equal potential are known as equipotential lines. Cleverly named. So these are lines with equal potential. And these equipotential lines are perpendicular to the electric field. So if I have some conductor and I'm trying to figure out the direction of the electric field, let's go with something a little bit more standard than what I have there. Oh, let's pretend we got a triangle. Triangular conductor. If I want to figure out what is the direction of the electric field, I know it's supposed to be perpendicular to the surface at the surface, but it might change once it gets away from that. What it could do is find the equipotential lines, which are actually much easier to measure. And I can find that all of those have the exact same potential. Now, you will measure it with something known as a voltmeter. But you'll find all the places where the potential is the same, and let's say I do find another potential here, so this might represent 3 volts, and this might represent 2 volts. 2 different equipotential lines, but the electric field needs to be perpendicular to that. So the electric field is perpendicular to the surface, and then at that point, and then at that point.
I had a question. Sorry,
Yes.
what are these lines exactly?
They're called equipotential lines. It's basically, if you move the charge anywhere along the equipotential line, it takes absolutely no work to do.
Okay.
In theory. I could have an electron here, give it a tap along the direction of the equipotential, and it can just sort of lap around.
Just go around.
Yeah.
Okay.
Are there infinite number of them?
Yes. Now, in the lab, when you're actually gonna find this, I think I asked you to find 7 equipotential lines. So you'll have 2 nodes here, which are 12 volts apart, and then you'll find like the 2-volt equipotential line, the 4, 6, whatever, things like that. It's prescribed.
So the electric field around this object, if you drew a line on the other side of that triangle, it would be perpendicular still.
It'd be perpendicular to the surface and then perpendicular to the lines themselves. At this point right here, where it starts to curve, that was horrible. Let's do one with a different shape. So if it's a square, I would end up with an equipotential line that looks. Ooh, no, better example. I got a plus and minus charge here. I'm gonna go backwards. Because I know my electric field should be going something like this. My equipotential line is perpendicular to the electric field, so my equipotential line will look something like that. It's not centered here because I've got another thing influencing it. If I just had a single charge, they'd be just concentric circles. But they're off there. Something crudely like that.
I'm sorry, why does it space out again? Because there's less, there's like less of the electric field on the right side. Well, no.
Well, these are sweeping out farther. I was trying to draw my black dotted line so that it was perpendicular to the electric field at that point.
Okay.
In some sense, if you think about it, I got a charge with these concentric circles of equipotential lines. I put another charge here, and it sort of shoves these this way,
That makes sense.
crudely. Now, a couple things here. One, I wanted to introduce this idea of equipotential lines, but I recognize we really have not talked about potential yet. That's chapter 19. But later on, when we get to chapter 19, you can look at this and go, oh, yeah, okay. We've known about this for weeks. Once more, the trouble of I want to introduce several concepts all at once. It all fits together. Questions? All right. We have talked about finding the electric field at a single point, from a single point. Let's expand that point. Suppose I have a spherically symmetric charge. Or a collection of charges. So this has some charge on it, Q. We'll assume it's positive for the sake of this. If I am inside, now the proof of this is calculus based, so we're gonna have to go for a concept way here. If I am inside, so spherically symmetric, let's make this a shell. Treat it like an insulator if you want to. Charges aren't gonna move. If I take a point closer to one side than the other, the charges over here are gonna have a much greater influence than the charges on the far side, because it's closer. except for the fact that I don't have as many charges over here as I do if I think about this as charges on the surface to the right of that point, charges on the surface to the left of that point. These charges have a greater magnitude, each charge I should say, each charge has a greater magnitude of the electric field at this point. And let's assume that these are negative charges all the way around. So these charges are going to have an electric field going that way. These charges over here will have an electric field going the other way. Each charge over here will have a weaker electric field because it's farther away, but I got more charges. And so there's this balancing act, and it turns out, and this goes along with something said earlier, that the electric field inside is equal to 0. It is subtly different than what I talked about before. Before I talked about electrostatic equilibrium and how charges will move to the outside. Here we're coming upon the situation, I guess it is pretty much the same thing. But the electric field inside is 0. However, if I'm outside, well, the electric field at this point is the electric field from every single point, every single charge that I have inside or on the surface here. So this has, they're all negative. I've got these electric fields going. Until you get tired of writing the lines. The electric field at this point is the sum of all the electric fields coming from every single charge along this distribution. It turns out that if outside a spherically symmetric charge, you can treat charge as a point charge. At the center.